My name is Eugene Lee, and this is my Physics 2212 Lab 2 report. So to start off, the purpose of this lab was to estimate the charge on a piece of floating tape using a Python model, where charges were evenly distributed across the surface of the tape instead of being just one point charge. The models and fundamental physical principles used were Coulomb's law, Newton's second law of motion, gravitational force, and the principle of superposition. As a brief preview of my results, the total charge on the top tape was calculated to be approximately 8.5 times 10 to the negative 9 coulombs. And we found out that the more charges we modeled, the higher the charge that we calculated. And then here's just a link to my code if you want to look at it. So for the actual experiment, Lab 2 was just an extension of Lab 1, where we used household objects to determine how much excess charge was on a piece of charged clear tape by using the repulsive electric force to balance out the force of gravity. And for Lab 1, we assumed that the tapes were point charges. The system was the pair of tapes, while the surroundings was Earth. And then for the initial condition, the top tape was drooping a bit, and then the bottom tape was held in place. Then when we moved the bottom tape near the top tape started to float a bit due to the repulsive electric force. And then here's my actual code for Lab 2. The top section sets up the physical constants. This middle section is a function to calculate the electric field at a given point due to a charged particle. And then this bottom function sets up all the charges on a piece of tape. Then here, the top two lines actually initialize specifically the top tape and the bottom tape. This middle section sets up the scale factors to apply to the arrows for easier visualization. And then this middle component is the most important part of my code. It calculates the force on each charge on the top tape due to every charge on the bottom tape. That's why there's two for loops. It sums that up, and then it prints that out with using these print statements, and then this section just sets up the arrows for the visual diagram. So in terms of my actual results, in Lab 1, using point charges, I calculated the charge magnitude to be around 1.67 times 10 to the negative 9 coulombs. And then in this lab, when I used 10 charges, I calculated the charge to be 5.25 times 10 to the negative 9, an increase compared to Lab 1. Then when I used 25 charges, it increased to 7.65 times 10 to the negative 9. 50 charges, I calculated it to be 8.45 times 10 to the negative 9. And then 100 charges, I calculated it to be 8.47 times 10 to the negative 9 coulombs. And then here's a graph of the amount of charges on a piece of tape versus the total charge. So you can see that it increases as the amount of charges increases, and it also looks to be asymptotic, approaching around 8.5 times 10 to the negative 9 coulombs. In terms of similarities between the point charge model and the line charge model, both of them calculated the net charge to be at the same order of magnitude, at around 10 to the negative 9. Both models also used the same core physical principles. Some differences, however, were that the line charge model has around 5.5 times the amount of charge compared to the point charge model used in Lab 1. The line charge model, however, is more precise because it's closer to reality since tapes aren't point charges. Some possible sources of error include that we didn't model enough charges because an actual tape has probably millions or billions of charges, though 100 probably was enough for our use case. And then other sources of error come from the data that we measured in Lab 1, since there were probably measurement errors when we measured the separation distance between the two pieces of tape, and then us touching the pieces of tape also decreased the net charge. So to answer the questions in Lab 2, the magnitude of the charge on one piece of tape as calculated by my computational model was 8.5 times 10 to the negative 9 coulombs. The assumption we made was that each U-tape had about the same amount of charge evenly distributed across the length of the tape. A resistance doesn't apply here since nothing's moving, and we didn't use the point charge model. To answer the what-if questions, If I modeled each piece of tape as a single point charge, again, it would have resulted in a lower total charge on the top tape. And the reason these estimates differ between the point charge model and the line charge model is because with more charges, there's more horizontal components of forces that get canceled out, resulting in a smaller vertical component of the electric force. That means we need a higher total charge to compensate for that. Well, that's it for this lab report. Thanks for watching.